In this final video, what I wanted to do is answer the extra credit question, the 10-point extra credit question. And what the extra credit question was asking for is that when you have a refrigeration process or an air conditioning process like what we see here, where there is not only water that's being condensed out, but also temperature of the air is being reduced. This amount of heat transfer, this amount of refrigeration in tonnage, typically is divided into two parts. One part is called the latent part, and the other part is called the sensible part. If we were to look at this on the graphics panel from the previous solution, we see that what we have is we started off with state 1 and state 2. This state 1 was the return air, state 2 was the outside air, and they mix together in a certain percentage and form state 3. That state 3 was then sent to a conditioning unit that brought the moist air out to state 4. And so what we want to do now is we want to look at what if we took state 3, which is the mixed state, and did the process going to 4 in 2 steps. What if we came down at a constant temperature and just removed the moisture so that we got to the level at state 4, and we determined the amount of refrigeration capacity for that process, and then we went ahead and did a reduction or a removal of heat that is called sensible heat to get us to state 4. And so what I want to do now is I want to identify a state 6. Okay, recall that state 5 is already identified as being equal to our water, our condensed water, but we're going to identify a state 6 that exists down at this point here. And so when I go back to my state panel, my states, I'm going to identify a state 6, which is at the 1 atmosphere of pressure, and I want it to have, in this particular case, it's going to be a moist air mixture. I have to switch back. Again, it's at the 1 atmosphere. It's a moist air mixture, and what I know about it is that it has the same mass of the dry air as we had in state 3. So that's a constant. Okay, but now what we also indicate is that the vapor level has dropped down to the vapor associated with the final condition. Okay, so that is the vapor associated with this state. So we have the dry air and we have the lower amount of vapor. Now, as I said, we want to do that in a constant dry bulb temperature approach. And so this temperature here is the temperature at 3. And so after it got mixed together, we then have a process where we stay at that same temperature, we remove the moisture, and we come out at the temperature, at the moisture level of the final. So that is our state 6. And if I looked at that on the graphics panel, that then shows up as this state right here. And so now we want to just finish off by looking at 2 additional processes. One going from 3 to 6, which is the latent process, taking out as much energy that we need in order to cause the water to condense, but stay at the same temperature for the air. And then the second process is from 6 to 4, where we then take whatever water vapor was remaining and whatever air was remaining and lowering it in temperature. And so with that in mind, we'll go back to our device panels. We'll set up a third device. And again, our third device is the latent device, and that's going to go from our state 3 to our state 6 that we just determined. Okay, and that's the constant temperature removal of moisture. But we also have to include the moisture in our energy balance. So we still have to have, the moisture coming out and being part of the overall energy balance. And so with this in mind, that's our process with no work. And we see if we calculate, we do a super calculate and go back to the device panel. It then tells us that that process required 1.033 tons. Okay, again, this process here, which was 1.789, this was the total heat transfer. And then this is the portion due to taking out enough energy to lower the amount of moisture. And then we want one last process, and that last process now is taking us from state 6 to the final state 4. Again, no work, and we see that it will then calculate that the amount of tonnage is 0.75. And so now this 0.75, in addition to 103, adds up to 178. And so the answer to the extra credit problem is that the latent heat and tonnage is 103, and the sensible heat and tonnage is 0.75. If one was interested in what they call the sensible heat ratio, it would be this magnitude divided by this magnitude. And that would then give you the sensible heat ratio. What portion of the heat was required to just basically cool the flow down, as opposed to the total amount that also is taking energy out of the latent phase of the liquid itself. So that is the end of the extra credit for this test.